This is some exam feedback for one of my parts of the Evolution of the Living Earth exam. So this is for part B. So this is just for the global and environmental change part. So I have another video for the biogeochemistry part, which you should be able to find as well. So before I go on and look at the individual questions for the exam, just again some generic advice about how you should go about trying to attacking an exam and going about getting as many marks as possible. So really, first of all, you should really read the question. You should do this if you've got an exam where you can choose which questions to do. Obviously, you read the questions thoroughly to identify which ones you think you can do the best. And then each question will either be explicitly split up into parts A, B, C, D, or so parts 1, 2 and 3 or something like that, or if you read carefully each of the sentences in the question, those will have different clauses in which will require different parts to be answered, and we'll go on and show some examples of that in this feedback video. And it's a good idea to, once you've chosen which questions you want to do, just to jot down in your answer book quick answers to those that get across maybe the few key points, some bullet points, or just some one-word answers that are at least going to get you some marks for each part of every question. And you can then go back and fill in those later on. So it's okay to leave lots of space in your answer books. And when you're answering the questions, it's really important to be specific. So I've used this term "be specific" here, but what that really refers to is answering the actual question that's been asked of you, not just writing down something that you can remember from the lectures that is kind of vaguely relevant to the question, but you need to answer the actual question that's asked of you. Okay, and then this embellish, if time allows, is you can go back once you've completed the exam and fill in parts of questions where you think you can add more detail. So you should never ever leave an exam early. You should always go back and try and add in to your answers if you can. Okay. Right, so this is the first question of part B. So this was a question involving one of these simple models of the Earth's temperature. So we give you this first of all part, so the simple one-layer model of the Earth's atmosphere. We give you this equation, okay, and this equation is specifically told to you, if we just go, get myself a pointer, okay, so this is an energy balance equation, and specifically it's at the top of the atmosphere. Okay, and we give you this equation here, and then we ask three parts of those equations. Okay, so just go through those in turn. So bear in mind, it's a good idea to have a look at the marks. So probably look at 25%, 50%, and 25%. So you should really be thinking about the bulk of your answer. You should be concentrating on this part B here. This is where most of the marks can be. So first of all, define all of the symbols used in this equation. Now, I'm not going to go through exactly what these all are here, but just to identify what the question is asking of you, it's these things here. So these are the symbols. I just want you to define them. Okay, so the term define here in the question is just what they are. So you don't need to go into a great detail. If it said describe what all the symbols mean, then we could maybe have a more fuller answer. Okay, so you just needed to identify what each of these terms here actually mean, and importantly, including units. So quite a lot of people missed out on some easy marks here by not including units. For instance, the temperatures here, surface temperature, and the temperature of the atmosphere, these are in units of Kelvin. Okay, so you should think about what you could have given for an answer to that if you didn't get that many marks for it. Okay, so this part of the question was not answered so well by many people, and quite a lot of that came down to not really answering what the question was asking of you. Okay, so first of all, the question asks, describe what each of the three terms in this equation represent. Okay, so we've got to describe, okay, so that we want a really fuller answer here of going through the detail of what each of these parts of the equation actually mean, rather than just defining what they are. And we were asking them what they represent. Okay, so first of all, I think the key thing is that quite a lot of you didn't really identify that the three terms are not the individual symbols, so not just the solar flux here, but the whole term. We want to know what each of these things are. Okay, so one of the things that I don't think anybody did was draw this diagram. So this is always a good idea to include diagrams in your responses in questions like this. But this is a diagram from the lectures, and you can use this to describe, for instance, to go through and explain, so to describe what each of these terms mean. Okay, so we're looking at a balance at the top of the atmosphere. So we're basically looking at the top of the atmosphere up here. Okay, and so for instance, we could look at the first term here. Okay. So this is the energy balance between stuff coming in and stuff coming out, okay, of shortwave radiation. Okay, so it's the amount of shortwave radiation the Earth receives minus the amount that is reflected. Okay, in this case, in the diagram, it looks like it's reflected from the surface, but this also includes reflections from clouds in the atmosphere as well. So you could have another arrow like that up there. Okay, and you could go on and embellish that with things like it's the shortwave radiation. We've got this term divided by 4 in here, which basically is because the Earth is a spherical object, and it receives solar radiation due to the area of basically the Earth's shadow, but that is spread over the surface area of the sphere. Now, you can then go through this on this whole, each of these things here. So you could go on for this guy here, okay, and then explain that this is the energy emitted from the Earth's surface, okay, that makes it through the atmosphere without being absorbed. Okay, so that's what this 1 minus here is. So if we didn't have this minus E, this would just be 1 times the Stefan-Boltzmann constant times the temperature of the surface, which is the amount of energy that is being emitted from the Earth because of the temperature of the Earth. But not all of that gets up here to the top of the atmosphere, so we have to take away that which is absorbed due to the emissivity or the absorptivity of the atmosphere. So one of the things that quite a lot of people did is they just described the maths of these equations. So they said, for instance, for this guy here, they said they'd identified what all of the parts of the equation were. They said that this represents the emissivity times the Boltzmann constants times the surface, well, times the atmospheric temperature raised to the power 4. That's not describing what the equation represents. Okay, what you would need to do is say this part of the equation here, this part of the equation, this represents the energy emitted from the atmosphere due to it having a temperature, and the emissivity basically represents the fact that the atmosphere is not a true black body, so it doesn't emit as much energy as it would if it were a black body. Okay, so you need to go into a little bit more detail than just describing the maths for this part of the question, and it would have been really helpful if you'd have had a figure to help explain what each of these 3 terms meant. Okay, so the next part of is just looking at for each of the parameters for the emissivity and the albedo, give an example of how these have changed in the geological past. Okay, so we're looking for an example for the emissivity and one for the albedo, okay, and how they have changed in the geological past and how they've affected the temperature. Okay. Okay, so moving on to question B2. Okay, so this is really a question all about the Milankovitch cycles. So the first part of the question, describe how changes in the Earth's orbit around the Sun govern changes in the Earth's average temperature and the spatial and seasonal distribution of incoming radiation. And I think quite a lot of you identified that what was required here was a description of eccentricity, obliquity and precession. Okay, bear in mind that this is a 70% part of the question, so there's quite a substantial amount of stuff that is required here, and we're not just looking for a short answer because we're really asking people to describe how the changes in the orbit, so we describe the changes in the orbit. Okay, so that's, for instance, the eccentricity is the deviation from a perfectly spherical towards an elliptical orbit, but that doesn't describe how the changes affect the Earth's temperature, okay, and particularly the spatial distribution of that temperature and the seasonal distribution of the temperature. So we're not just looking for changes in the average temperature, because in fact the Milankovitch orbital variations don't really change the total or the average temperature of the Earth that much, but they do have big impacts on the spatial and the seasonal temperatures of the Earth. Okay, so these are some of the slides from the lectures which would have been relevant for this answering this question, and we're really kind of looking here for kind of basically a description of how you go from these orbital kind of variations to how the distribution of temperature or distribution of heat around the Earth changes. So, for example, the obliquity. So that's this obliquity of the Earth. So this is basically how much it's tilting. Okay, so you'd get some marks for that, but the important things to get are that it basically affects the magnitude of the seasons. So when the Earth's axis is tilted over more, we get much warmer summers and much colder winters. Okay, and those effects are the same in each hemisphere, and they have a period of 41,000 years. Okay, so all those things would have got marks, but the key thing we're looking for is that how it affects the seasonal distribution of energy, and that's important for the next part of the question. Okay, so how do climate feedbacks affect the outcome of these orbital climate forcings? Okay, so this is one place where quite a lot of you went a little bit astray with not being specific enough with your answers. Okay, so quite a few people just mentioned a whole bunch of climate feedbacks, okay, but we're specifically looking for how climate feedbacks that can act on these orbital climate forcings, okay? And the thing to remember is that the climate forcings due to orbital variations, they don't really change the average temperature of the Earth so much. They don't change the average temperature, but they do affect how strong the seasons are, okay? They have a big effect of those seasonal variations at high latitudes. And the important thing is the timescales that these forcings act on. So they act on forcings of maybe 10,000 years up to hundreds of thousand years. So if you were to describe a bunch of climate feedbacks that occur on very, very short time scales, okay, or very, very long time scales. So quite a lot of you talked about the weathering feedback on carbon dioxide and global temperatures, which is important for the long-term history of Earth's climate, but acts too slowly to be relevant for these orbital climate variations. That's something that's relevant on many millions of years timescale, but not on the tens to hundreds of thousand years timescale so much. Okay, so the third question here. So since the 50s, the annual average CO2 concentration in the atmosphere has risen. Okay, but the surface temperature has not closely matched that rise. Okay, so this has got two parts to the question here. So the first part, because we're really looking for, there are two parts to this question. So this is one of those things where even though I've split this question up into parts A and B, within part A there are still two parts. So the first part is, how has the rise in surface temperature differed, okay, from CO2? And then the second part of this question is, why has it not matched exactly? Okay, so there are two parts to this question. So if you didn't describe how they were different and then explain why they were different, if you just explained why they were different without describing how they were different, you missed an opportunity to get marks there. Okay. Once again, this has got quite a high proportion of marks associated with it, so it's worth going into some detail. So these are the two records that we're thinking about comparing, and it's quite surprising that again nobody thought about sketching out these two records. Okay, so we've got since this is a graph from the 60s to the present, and this is kind of the 50s to the present. So similar kind of scales here. You can see that the rise in CO2 is almost monotonous. Okay, it's very consistent going up here. Okay, the other thing, so if you look at the temperature rise from the 50s, there's not much of a change, and then it starts to kind of ramp up. Okay, so the other thing to notice is that there's this, oh, that's a really bad, but there's this annual up and down on the CO2. There's also variability in the temperature, but it's not of the same period. Okay, so it has a different kind of frequency. So these ups and downs in the temperature, okay, they occur over multiple years. Okay, so they're got a wavelength in terms of time of maybe 3 to 7 kind of years, something like that. Okay, so they're not the same variability. Okay. and the variability is much less uniform than it is for the CO2. So those are the differences we're looking at, okay? And we need to go into explaining then why they haven't matched. Okay, so there are multiple reasons for this. So some of these slides are then taken from the lectures. There are other forcings affecting temperature, not just CO2. So we've got other greenhouse gases, which have perhaps, so they've got methane here, nitrous oxide. So things like this have acted to warm the planet, as well as the CO2, which is the most important driver. Okay, which is why the temperature and the CO2 records do both go up over this time, so they do to a certain extent match, but there are other drivers of climate going on at the time. Okay, and the other thing that's been happening, other than different greenhouse gases changing at different rates compared to CO2, we've also got these things called aerosols, which have a cooling effect. Okay, which can be either through volcanic emissions or through anthropogenic aerosols, such as the burning of coal producing sulfur emissions, which was responsible for the suppression of temperature rise in the 50s, 60s, and early 70s. You could have gone in to look at some of the other variability. So some of these, if you can see here, we've got the solar cycles here that are affecting temperature independently of CO2, but to get some even more marks, you could say that there are these other forcings, but they are small compared to the importance of CO2. Okay, and the other thing that you could have gone into talking in this question is looking at some of the internal variability of the climate system. So some of the variability that we see in the temperature record is due to kind of natural oscillations in the climate system, such as the El Nino Southern Oscillation here. So when we've got El Nino conditions, so this is El Nino conditions here. Okay, we can see that the ocean temperature is kind of much more higher in the Pacific. The warm pool is spread out much further to the east over to this side here than it is with La Nina conditions, where all the warm water is piled up over in the west. Okay, and then you look at the temperature anomaly maps, you can see that this causes there to be an anomalously large warm region in the ocean when we have El Ninos. So when we're in El Nino states, which are kind of these periods here, we can correspond those to kind of warmer periods in the Earth's kind of global temperature. So some of this interannual variability is due to El Nino. Some of the deviation from the straight on expected CO2 rise is due to some of these other forcings that are affecting climate. Okay, and then kind of the last part of this question is what else can we look at to explain, or what other evidence is there essentially for global warming? Okay, so other than the surface temperature record, okay, so we know a describe here. Okay, so how other data sets can be used to show the warming of the planet. Okay, so here once again I've put this little tag up here, be specific. So quite a few people wrote about proxies that can tell us about maybe past CO2 levels. Okay, so which is maybe a proxy for the amount of carbon dioxide in the atmosphere, or a measure of the amount of carbon dioxide in the atmosphere from ice cores. Those are not kind of data sets that show the warming. They're data sets that show the forcing that's then causing the warming. So we're kind of really looking for things like increased storminess. Okay, like this one here. It's kind of maybe a little bit controversial that increased storminess is actually a result of global warming. But things like changing the timings of bird migrations, or kind of the flowering plants, snow-free days in the Alps, okay, when the skiing kind of like goes all wrong, increased desertification, sea level rise. Those are all kind of a good list of things to say. You might want to then describe how. Okay, so this is describing how. So in the case of sea level rise, you could say that in a warming world, the oceans will expand, ice will melt from the ice caps, but also from continental ice, from glaciers in lower latitudes, continental water storage due to kind of desertification, that will also release water into the ocean. So you need to describe how as well as just listing. Okay, quite a few of you went and talked about proxies. So things like measurements in ice cores of isotopes. This is an ice core here. This this is kind of representing isotopes, or lots of people talked about tree rings, and that's kind of okay, but those kind of records aren't really used since the 1950s, when we have more direct evidence from different places around the world. Okay, so that goes skimmed over some of the parts of the exam where hopefully you can see where you might have picked up more marks this time, or maybe next time, and get a better idea of what we're actually looking for when we're asking questions. Okay, so you can kind of maybe now decode what we're actually asking for when we say describe or define, or when we're putting multiple parts of a question into one sentence. We're looking for different things. Okay, to make sure that you don't miss out on some of these potentially easy marks to get by just not answering the question. Okay, so I hope this has been useful to you. If it's not, then there'll be a teaching office will organise a feedback session where you can come and find out more about your specific exam results and what you've written, and that will be announced sometime later on in the term. Okay, bye bye now.